my classes on fundamentals of electrical engineering, to which fundamental happens to be the transients. So we are moving into the fourth session on transients, and in this case we will be looking at a few problems which might have both inductors and capacitors, but whatever we have been discussing so far would apply, okay, to some extent. Okay, let's see where the differences creep in. Okay. So the first circuit itself, okay, as was mentioned earlier, have a look at the circuit first. Okay, look at its complexities, and if you see some complexities, remember that you can always have simple solutions. That's point number one. Point number two happens to be that because it is transients, how do you recognize a transient? How do you recognize a problem which occurs under transients? By seeing a switch. So once you see a switch and a DC power source, okay, as is obviously given in the circuit, then remember that at steady state, the inductor is going to short out and the capacitor is going to open out. And this would be your perspective as you observe the problem. So what we see here, we see that there are two inductors, 1 millihenry each, which will, of course, at steady state short out. But this the 1 millihenry, the vertical one will give a path for current to flow, because the capacitor in parallel with it would have opened out. Okay, similarly, it would be the 1 ohm resistor down below which would be carrying the current because the 5 microfarad capacitor with VC across it, okay, perhaps we are supposed to find out VC, would have opened out. Okay, so this is the context, and 10 volt source as was mentioned earlier, and the switch is going to close. Okay, so now let's read the problem and see what is required out of us. In the circuit shown in the figure, the switch is closed at t equal to 0. Okay, so everything was good before. There was nothing happening because there is no input, there is no voltage trapped in the capacitor. Nothing is given. The steady state value of the voltage is shown, is asked. Okay, so once the switch closes and at steady state, the first inductor shorts out. So if a current emerges from 10 volt, if it emerges, okay, then it flows through the shorted 1 millihenry. It passes on to the 1 ohm immediately afterwards. Then it will disregard the path through the 5 microfarad capacitor because it is opened out, but it would flow through the 1 millihenry in parallel to it, 1 millihenry inductor in parallel to it because it's a short, and thereafter then it would proceed through the 1 ohm resistor. So the total opposition to the 10 volt source, or to the current that comes out from the 10 volt source, is simply 1 ohm and 1 ohm. Okay, and so what happens is that the potential divider between the two, and so the capacitor sees this particular potential, that is the voltage across the 1 ohm resistor, which is half of the 10 volt, which is 5 volt. Okay, it's a very simple problem, and it's just observation, and some concepts that were discussed would alone suffice to do this particular problem. Okay, so moving on to the second problem. I hope we noticed that it's an AC case this time, okay, a little different from the previous problems, okay, and the voltage given has a maximum value is 150 with an omega as 377 plus an angle theta. What is this angle theta? The inception angle that we talked about, okay, or in other words, this voltage is going to come on at omega. Okay, this should have been a theta, should have come on at 377t as equal to theta. Okay, so that's the situation, that the angle should have been 377t at theta. Okay, so now let's read the problem. Okay, of course, there's a resistor of 3.77 ohm. That's interesting because it's just like it has some relation to 377. No doubt, no, of course it has, because L is given as 10 millihenry and omega L for an AC case, it has to be omega into omega is 377. The T is missing, 377, and then again into 10 raised to minus 3, that is milli. That is 0.37 into 10, 3.6. So inductor, the reactance of the inductor and the resistance value happen to match, or in other words, the power factor angle is going to be 45 degrees. Okay, so even before reading the problem, we realize that theta now has to be 45 degrees such that it can avoid the transients, or it can have a maximum value. Let's see the circuit shown below. The switch is closed at t equal to 0. The value of t 10 degrees, which will give the maximum value of DC offset of the current at the time of switching. The DC offset is what we talked about in the earlier session, wherein we had e raised to minus t by tau, that tau is equal to L by R in this case, and we had sine theta plus 5. Okay, so here we should have what is called as we shouldn't have sine value as equal to 0, but it should be 90 degrees. So whatever be the case, it's going to be now minus 45, such that minus 45 and minus 45, because it's a lagging angle, should correspond to 90 degrees. Okay, together should give 90 degrees. I hope this is clear. Okay, so the third problem. Okay, third problem, I suppose we see both an inductor and a capacitor. Okay, it's a little different. Should be a little different, but we shouldn't have any problem. There are two switches too. One switch is available across the inductor. Another switch seems to be in the path of the capacitor, and the capacitor seems to have 10 volt across it, and there are two resistors, R1 and R2, equal and 10 ohms. Okay, there isn't any source there, but there's a current through the inductor, 10 amps. This could be the charged inductor and the capacitor working together to see to it that the transients are promoted. Okay, so let's read the problem. In the circuit shown in the figure, switch S1 is initially closed. So what do we have here? When switch S1 is closed, as you read the problem, it's better to analyze then and there. Okay, so if the switch S1 is closed, what happens is that if there was any current trapped in the inductor, it would flow through the short circuit. Okay, and another important aspect, of course it is ideal, but the ideal condition happens to be that this energy will not get dissipated at all, because there's no resistance. The switch is supposed to be supposed to have zero resistance, though it is never so. So this energy continues, so the 10 amps continues to flow without any dissipation or without any lessening of this amount. Okay, and so S1 is initially closed and SW2 is open. So the capacitor is standing there with the charges trapped in it, ready to discharge as and when it gets a circuit. Okay, the inductor L carries a current of 10 amps and the capacitor is charged to 10 volt with polarities as indicated. Okay, as switch as indicated, SW2 is closed. Okay, at t equal to 0 minus. This 0 minus and 0 plus were earlier big matters of concern. Now people don't talk much about it, but then 0 minus is just immediately, okay, because before the molecules touch, and then 0 plus is after the molecules of the switch, the two portions of the switch touches. Okay, so we have SW2 is closed at t equal to 0 minus, and SW1 is opened. Okay, so actually the current is let loose. Okay, and the voltage is also allowed to discharge. Okay, the current is let loose because it was flowing, it was circulating through the switch S1 W1, but SW1 is now opened out. Okay, is opened at t equal to 0. The current through C and the voltage across L at t equal to 0 plus. Okay, so all aspects now come into the picture, but I would like to point out two more concepts here which are going to help you for the transients. One is, of course, that what is the equivalent of the inductor at t equal to 0 plus. Okay, 0 plus. Okay, it is working as a current source. If it has a current with inside it, it is working as a current source. What does current source mean? It means that in the same direction as the 10 ampere is there is a voltage as well. Okay, then it becomes a source. Okay, and the inductor, okay, without any source content will be in parallel to it. Okay, if this is the case for the inductor, what about the capacitor? It is its dual. Okay, so it will have a voltage. Okay, and the capacitor without any voltage will be in series with it. If the inductor was in parallel to the current source, the capacitor would be in series with the voltage source. Okay, so whatever voltage is trapped inside the capacitor is now coming as a series source. Okay, and what would be the direction of current? It would be such that both have the same direction, both the voltage and the current have the same direction, because now the capacitor is becoming a source. This is the idea inherent in the fact that both the inductors and the capacitors are considered to be energy storage devices. So once the stored energy is given a chance to discharge, then it acts as a source of this particular energy that is stored within it. Okay, so this is an important point that I would like to add to transients. That is, the status of the inductor at t equal to 0 is of an open circuit. Okay, and it has two components: a current source, okay, in parallel to the inductor value. Okay, of course it's a source, so the current and voltage directions are the same. And on the other hand, the capacitor, it's a short circuit. At t equal to 0, it is a short circuit ready to discharge. Okay, and so it is considered to be a capacitor free of all voltages, in series with the voltage source, the same direction, and the current and the discharge direction of the current and the voltage source will happen to be the same. Okay. So this is it. Okay, so now let's see how things happen. Okay, so now when the path is free for the inductor, okay, what happens is that the 10 ampere source that is there in a series with the opened out inductor now gets two paths. Okay, one is the 10 ohm resistor on the side, that is on the left side, which is R1, and then it is R2, and the capacitor is now acting as a short circuit. Okay, because as was mentioned earlier, so now we are having 10 dividing into 2, 10 ohms on one side, 10 ohms on the other side, take them out, so it's 5 amps through the capacitor. This is what is asked. What is the current released through the capacitor t equal to 0? Okay, now what about, so that part has been resolved. That is, the inductor current is now dividing into 2. It will not flow through the inductor which is opened out, but it will flow through the capacitor, and in a direction such that it matches the direction of entry of the or in other words, it's charging the capacitor. Okay, it has to match the same direction as the original current 10 amps. Okay, so it will be so the circuit definitely tells us that it will be charging the capacitor. Okay, so the capacitor is also discharging. So what is going to happen? So there's going to be an opposition of two currents. Okay, one is the discharge current, and another is the charging current. So what about the 10 volt source? Okay, what does it see? It sees that the inductor is open, so it will not follow that path. On the other hand, the two 10 ohms now happen to be in series. So 10 volt is now opposed by 20 ohms. That is half ampere. So 5 ampere was entering and half ampere was leaving the capacitor. So in total 4.5. Okay. So that's one part of the solution. What else is asked is the voltage across it. Voltage across the voltage across the voltage across the capacitor and the voltage across the inductor. Okay, so inductor now happens to be across R1. Okay, so R1 has two currents. One is the 5 ampere release from the inductor, and other is the half ampere release from the capacitor. Both are in the same direction. So it is unlike in the capacitor, they are in the same direction. So 5 plus 0.5, 5.5. 5.5 into 10 ohms, that's 55 volts. Very simple problem, but then you will get 2 marks because this is one of these kinds of problems are problems that fetch you 2 marks. Why? Because there are two answers. Okay. So let's go to a very interesting circuit. Okay, the circuits that are given as a component of transients happen to be very, very interesting. They are also practical circuits. More often than not, you'll be able to use this. This is a beautiful circuit that I always wanted to implement. Okay, what is there? There's a 10 volt source. There's a 1 ohm resistor in series with it. There is an inductor and a capacitor and a diode in between. What does the diode do? Diode provides what may be called as a one-way wall. Okay, so long as the diode is forward biased on the right hand side, it conducts, otherwise it stops. Okay, so now all that we studied become useful here. And of course there's a switch. A switch means a transient. Okay, so let's read the problem and see. Okay, so the inductor is 1 millihenry, the capacitor is 10 microfarad, and the capacitor and the voltage across the capacitor is shown with a particular direction as we see. Okay, so now let's see, let's read what the what is required out of us. The switch S in the circuit shown has been closed for a long time. Okay, so the switch is closed for a long time, and so what happens? We see that the inductor gets charged. Okay, in what direction? We are having on the left side a positive is marked, the positive sign is marked, so that's the direction in which the inductor gets charged. What does it get charged with? It gets charged with the current. And what is that value of current? It is 10 by 1 because the inductor has shorted out, isn't it? The inductor has shorted out. It's a DC source which is being applied, so it is 10 amps. So 10 amps is now flowing downward through the 1 millihenry inductor, and the top part is, of course, as is always the case, the point of entry is considered to be positive. Okay, now things are changing. It is opened at t equal to 0. When at t equal to 0, when the switch is opened, the current will have to follow the same path as was given. Okay, this is constant flux linkage theorem. The current cannot change. The current cannot suddenly change its direction, but the voltage changes. Why does the voltage change? Because now it's a source. Okay, it has to. That is what is, okay. L di by dt, a sudden change. Okay, so we are having a voltage. Okay, and this voltage is going to be such that, as shown in the as shown on the right side of the inductor, it is going to be positive on the bottom terminal, unlike when it was charging. Okay, so this is what is happening, and the switch is open, and this current now has to get a release through the shorted out capacitor. Capacitor at the beginning is 0. Okay, it's a short circuit, so it is going to discharge through the through the capacitor. Okay, so now what is asked is that is equal to 0 and remains open after that. Assume that the diode has 0 reverse current and 0 forward voltage drop. Okay, so it's an ideal diode. Okay, but still this is the way that we build up oscillators. Okay, in this case it's not an oscillator. So what happens is that this current now flows through the capacitor. Okay, and then and charges the capacitor such that the bottom terminal becomes positive and the other terminal becomes negative. And when these at a particular time, what happens is that the capacitor becomes reverse, the diode becomes reverse biased, and so no more current is possible. So there's a voltage build up across the capacitor and it cannot discharge. Okay, because it cannot discharge in the reverse direction, as is obvious from the biasing particularities of the diode. Okay, so what is the voltage that is obtained here? Okay, so how do you, so now here we are having a particular system wherein a resonance is being set up. Why is the resonance being set up? Because we are having an inductor capacitor connected in series in the circuit. On the right, the left side circuit has opened out. So let's find out what is the frequency of this happening. Okay, this is an oscillator circuit. Okay, so we are having 1 millihenry and 10 microfarads. So 1 by 1 into 10 raised to square root of 1 into 10 raised to minus 3 and multiplied by 10 into 10 raised to minus 6. So we are getting omega is equal to 1 by root LC is giving telling us that omega is equal to 10 raised to 4. Okay, and what is the voltage across the capacitor? It is the same as the voltage across the inductor. Okay, that's why we are having resonance. And okay, so what is the voltage across the inductor? It's the same as equal to 10 amps is flowing. Okay, 10 amps into omega. And what is omega? Omega is 10 raised to 4. Okay, or you can use the capacitor also. Okay, so I have used the capacitor here and I'm discussing about the inductor. Okay, because the voltages happen to be the same. Okay, so you can see that okay, it is 10 into 10 ampere into omega. Omega is 10 raised to 4 and 1 millihenry. So that gives us 100 volts. So you give 10 volt DC source, you get 100 volt on the other side. A transformer kind of thing. And if this switch can be switched on and off regularly, we'll have a transformer. That is, you give 10 volt, you get 100 volt. Beautiful circuit. Okay, and both aspects were discussed. That is, the capacitor voltage or the inductor voltage happen to be 100 volt. Okay, so from 10 volt, you create 100 volt out of a particular kind of usage of inductors and capacitors and a diode. Okay, so a similar concept is now examined perhaps in the question, in the next question, which is 5. An ideal capacitor is charged to a voltage V0, just as we saw here, and connected at t equal to 0 across an ideal inductor. So ideal capacitor, ideal inductor means that we are having an oscillator. Okay, what do you mean by an oscillator? It has a resonance frequency. Okay, the circuit now consists of a capacitor inductor alone. If we let omega naught is equal to 1 by root LC. So it's already given that we are having omega naught is equal to 1 by root LC. The voltage across the capacitor at t greater than 0 is, of course, it's an oscillatory circuit. So it's either cosine or sine. And what is and we also have omega naught. Okay, because that's the frequency of oscillation and t. Okay, and of course at t equal to 0, what we realize is that we have the voltage across the capacitor at t greater than 0. Okay, so what should we have? We should have that voltage. The capacitor is now an assembly with the voltage source and the capacitors and the capacitance CV. So that is the totality, and the voltage is given by V0 into cos omega 0 t. Why? Because at t equal to 0, cos is equal to 1, so V0. So the entire voltage that has been charged to the capacitor is now available across the capacitor assembly. Okay, but that is just an equivalent circuit. But the physical capacitor still has V0, but this voltage is going to oscillate. Okay, and the inductor is going to help it to have this oscillating kind of voltage and current picture here. Okay, yeah, so that perhaps is similar to question number 6. So let's see, that's why I placed them together. Question number 6 says the LC circuit shown in the figure. Okay, of course we see the figure in this case. We didn't see the figure last time. So again, L and C are together and we are having 100 volts there. Okay, so the figure has an inductance L is equal to 1 millihenry and capacitance C is equal to 10 microfarad. We examined the same problem last time and we saw that omega was equal to 1 by root LC, which is equal to 10 raised to 4. Okay, 1 by root LC gives you 10 raised to 4. So omega is, of course, it's an oscillating circuit, so it is sine or cosine. Okay, and 10 raised to 4t. Okay, and the value is, of course, that is the source is 100 volt. For the circuit, the energy source is 100 volt, and omega L can be taken into consideration of 1 by omega C, because omega is already calculated. Okay, so at 10 raised to 4 and L is equal to 1 millihenry, so that gives us 10 ohms. So 100 by 10, that is 10. So 10 seems to be the answer for C and D. So 10, now cosine of sine. Okay, so what is asked is, let's see, we haven't read the problem yet. The LC circuit shown the figure as an inductance 1 millihenry and the capacitor, yeah, we went as far as that, capacitance C is equal to 10 microfarad. The initial current through the inductor is 0, while the initial capacitor voltage is 100 volt. Okay, initial current, because the inductor happens to be an open circuit with the current source in parallel with it, we don't have a current source here. The switch is closed at t equal to 0. The current through the circuit is, okay, so the current through the circuit is the same as equal to, at t equal to 0 it should be 0. Okay, because the inductor is right in the middle of things and it is an open circuit. So what do we have? We should have a sine value, because sine 10 raised to 4 t will give you at t equal to 0 value. Okay, so 10 is okay. 10, because we are having 100 divided by omega L or 1 by omega C, that gives us 10. Sine is why, because at t equal to 0, sine value is 0. 10 raised to 4, because omega is 10 raised to 4 and t. Okay, so many amperes will be flowing through the circuit, okay, which is now an oscillating circuit. Okay, so now we come to the seventh problem. Most of them look similar. They have an inductor capacitor. Okay, of course, as I said earlier in this session, mostly the combination of inductor and capacitor is being taken care of. Okay, the LC circuit shown the figure has an inductance. Okay, we already noticed whatever was happening, and it was the same as before. Okay, and there's a current, there's an inductor, there's a capacitor, and the capacitor has 100 volt charge across it. Okay, and the inductor is the same volt 1 millihenry, and the capacitance is still C is equal to 10 microfarad, or immediately omega is equal to 10 raised to 4. Okay, the LC circuit the LC circuit is used to commutate a thyristor. Okay, as I said earlier, transients have a big bearing on the power electronics of circuits. Okay, so commutate a thyristor which is initially carrying a current of 5 ampere. So we have shown a thyristor which is carrying the thyristor, the switch diode is clearly shown with carrying a current 5 ampere. Okay, from the anode to the cathode. Okay, and then there's a 100 volt source in the circuit as also 20 amps. Okay, and we also have the LC circuit which we earlier spoke about. Okay, and at t equal to 0, this circuit is now going to be utilized for perhaps switching off the thyristor, because now the direction will change. So 5 ampere will be opposed by the other whatever ampere that comes out from the inductor and capacitor combination, and so when they are nullified, the thyristor will close. Okay, so the thyristor will switch off. This is the idea that has been taken from transients to thyristors. Okay, long time back. Okay. So yeah, which is initially carrying. Okay, so the LC circuit is used to commutate a thyristor which is initially carrying a current of 5 ampere as shown in the figure. The values and initial conditions of LNC are the same as before. Okay, so we have already seen that the values of LNC and 100 volt is available across the capacitor. The switch is closed at t equal to 0. Which switch? The switch that is now in the 100 volt circuit. Okay, the forward drop is negligible. Okay, of course, if the forward drop is negligible, the time taken for the device to turn off. Okay, so now when both currents equate, we are going to have turn off. Okay, so 5 amperes are already given. Okay, now we need to have okay, of course 100 by 20 is giving us 5 amps. Okay, that's also true. And now even if it's not given, you can calculate that 5 amperes has now got to be opposed by the current that is emerging from the capacitor based on a sinusoid, because the current through the inductor and capacitor, when the capacitor is charged to 100 volt, as we saw earlier, it is 10 sine 10 raised to 4 t. Just in the previous example we saw that, and that's also written down here. 10 sine 10 raised to 4 t ampere is now equated to 5 ampere. Why 5? Because they both should be equal, such that you are having null current and the thyristor turns off or commutates. Okay, so we see that sine 10 raised to 4 t is the same as equal to 0.5. Okay, so what does it mean? It means that sine inverse of 0.5. What is sine inverse of 0.5? Please work in radians, because we are going to work with in terms of other values. We are not using degrees at all. Okay, so sine inverse 0.5 is pi by 30 degrees or pi by 6, and this pi by 6 has to be now divided by 10 raised to 4. Okay, to give us what is the time that is taken for both the currents to equate and commutate the capacitor. So obviously it's the same as equal to A of 52 microseconds. Okay, I suppose it's very clear that the utilization of transients in many contexts. Okay, I talked about a transformer. Now here we see an application for commutating thyristors. Okay, so let's come to the last problem in this session. wherein we are having again an inductor and a capacitor charged by a 5 volt source, and we are having at t equal to 0 the switch is being made, and the IT is shown, and L is 1 Henry and capacity is 1 Farad. Okay, and the voltage across the capacitor is VT and the current through the inductor is IT. Okay, so let's see. A DC voltage source is connected to a series LC circuit by turning on the switch S at time t equal to 0 as shown in the figure. Assume I0 is equal to 0. Of course, it has to be 0. V0 equal to 0. Okay, so it's not charged at all. Which one of the following circular loci represents the plot of IT versus VT? So it's IT versus VT. Okay, it's not time, but it is current. Current which is dependent on time, as also voltage which is dependent on time, pitted against each other. Okay, so what do we have? Where do we start? Okay, we can start from I0 is equal, that is at t equal to 0, because the axes are all t. Okay, so the axis of, because we are having a point, axes are not t. Okay, axes are IT and VT. Okay, we are having a point wherein both I0 and IT and VT are equal to 0. Okay, so that will be the origin. Okay, so origin, so all of them start at 0. Okay, then what happens? Then slowly we see that the capacitor is going to charge. Okay, based on the current, the capacitor is going to charge. So the capacitor is going to get a full voltage. Okay, and then what happens is that once the capacitor is fully charged, now we are having we are going to have a reversal of the current. Okay, so we'll see that wherever we are having the capacitor getting fully charged to a full value, and then we are having a reversal of the current, as is applicable for B and D, as also to some extent, but of course the inductor and the capacitor is not getting charged here in A. So B or D. Okay, so how do we see what? Okay, so now the capacitor. So which direction is the capacitor charging? It's charging the same direction as shown here. Okay, as VT. So obviously B is correct, because in the other case, in D case, we are seeing that the capacitor is getting charged in the opposite direction of minus VC is going to be put on. Okay, but as per the IT, as also as per 5 volt, we see that the capacitor is going to get not just 5 volt, it's also going to get 10 volt. Why is it going to get 10 volt? Because when the inductor reverses the current, what is going to happen is that, you know, when the inductor when we are having the voltages being the same, such that we are going to have a sort of a switching kind of thing, then the inductor voltage is going to change. The current direction is not going to change, but the inductor voltage is going to change. So the total voltage applied across the capacitor is now going to be not 5 volt, but plus 5 volt, another 5 volt which is available across the inductor. Okay, so we are having 10 volt here. Okay, so that's the reason why you see that the radius is going to be of dimension equal to 5. So the center is going to be at 5, and be appropriately gives a locus for the voltage current pattern as we switch on a 5 volt source onto an LC circuit. Okay, so I suppose mostly we have talked about the inductor capacitor combinations, giving rise to very interesting circuits and very interesting application. Okay, so the phenomena is essentially, mostly we talked about the sinusoids, etc. The sinusoid picture emerging as a result of L and C. We also talked about we also talked about a very important concept that needs to be remembered, in the sense that what is the equivalent of an inductor at t equal to 0. Okay, it's an open circuit with a current source in parallel to it. Okay, and because it's a current source, both the current and the voltage directions happen to be the same. Or in other words, whenever switching occurs, the inductor, if it had a current flowing through it, the voltage changes, the voltage direction changes. Okay, such that to match the concept that it is working as a source. Okay, the dual happens to be the situation with respect to the capacitor. The capacitor starts off as a short circuit. Okay, so it has the voltage source in series with it. So the discharge direction of the current, as also the direction of voltage impressed across it, happen to be the same. Okay, so one is an open circuit, the other is a short circuit. One gives rise to a current source, the other gives rise to a voltage source. The current source happens to be in parallel, the voltage source happens to be in series, but the directions of both the current and voltage in both cases happen to be the same. Okay, so this is a very important concept that we need to remember. And of course, we tried to repeat what we did in the last session, wherein we talked about but of course a little differently. This time we wanted the transient to have a maximum value, so we tried sign for sine 90. And why is it minus 45? Because omega L gives rise to a lagging current. Okay, so lagging current means that we are seeing that angle is negative. Okay, so both angles, if they are negative, minus 45, give us sine 90, sine minus 90 or whatsoever, and that will give us a maximum value. Okay, so that's all that is there from this session. Let me hope that the transients, okay, will remain the sparkling component of electrical engineering to all of you, because it will be visited several times. Thank you.